Okay, any questions? Yes, there is one question over there. He has a question. So you see, this is your question, right? So we said that the potential energy of a given system is 1 over 2 Qi times the potential at that point Qi, summed over all the charges, right? How do we get this one? Well, we started from just a few examples. We said that, okay, let's imagine two charges, Q1 and Q2. In this case, we know that the potential energy is 1 over 4 pi epsilon 0, Q1, Q2 over R12. This is the potential energy of the system, which we can also write as 1 over 2 times Q1 times 1 over 4 pi epsilon 0, Q2 over R12, plus 1 over 2 times Q2, 1 over 4 pi epsilon 0, Q1 times R12. Okay, so this is equal to 1 over 2 times Q1, but this is nothing but the potential created at the position of Q1 by the other charge, plus 1 over 2 Q2, and this one over here, in this parenthesis, is the potential created by Q1 at the position of Q2. So it's the potential at the position of Q2. So this is for two charges. Then we repeated it for three charges, and we saw that the pattern is quite general. In fact, you can also derive it for arbitrary number of charges, and you will see that this is the final expression. Now, to see a derivation for the general expression, you see the general potential energy for an arbitrary set of charges is this one, Qi, Qj, divided by 4 pi epsilon 0, and the separation between the I and j. Now, how do we calculate this potential energy? We bring the charges one by one. So when there is if we have the first charge, there is no potential energy. Then we bring the second charge, then we talk about the potential energy between charge 2 and 1. Then we bring the third charge and we add the potential energy between 1 and 3 and 2 and 3, etc. So in this sum, we are summing over all the charges, or let me write it in this form. We are summing over all the charges, but I should be less than j. So when we are bringing the jth charge, only the previous charges are already there. So this is, we have this restriction. But this is also equal to sum over ij, j less than I, qi, qj, divided by 4 pi epsilon 0, rij. These two are the same thing. So here I is small, here j is small. So if they are the same thing, then I can just write the u as the sum of these two, I less than j plus ij, j less than I, of qi, qj, divided by 4 pi epsilon 0, rij, times 1 over 2. This is the origin of the 1 over 2. So it's basically this thing done for in a more, let's say, more complex looking way. But what I did over here is exactly what we did over there. So if we don't have this 1 over 2 and sum over all the I and j, we are kind of double counting, because we are counting the work that when we bring the jth charge from infinity when the ith charge is already there, we are also adding the work that we have to do to bring the ith charge from infinity when the jth charge is over there. So to avoid that, we have to divide by 2. Other questions? that's something else, and we can discuss in the break. Other questions? Well, you see, when I look at your faces, I see that you are getting lost. I have absolutely no clue why you are getting lost. So unless you ask me or you tell me why you are getting lost, I mean, there's nothing much I can do. I don't want to lose you, but I mean, I don't know what to do. So if you just have any questions, if you are lost, I don't know. If you know where you were lost, you can just ask it and we can repeat it. I mean, probably most of you are just thinking that you are the only one lost. All your friends are understanding everything since they are not asking anything. But believe me, when you see all your faces from here, there are just a couple of you who are not lost. Somebody else, please. I mean, he also doesn't like it when I don't let him speak, but he's always the one speaking. Okay.
Imagine if we had a conductor, an armature, which had a cavity, and we chose in two cases, we chose a Gaussian surface, like one enclosing all on the surface of the conductor, and one which...
On the surface, the first one.
Yeah, the first one on the surface. And the other one, exactly, and the other one is a bit inside, and it's coinciding with the cavity. Do you understand what I'm saying?
You mean such a Gaussian surface?
Yes, and there is a cavity inside which the line of the Gaussian surface is half inside and half outside.
So here I have a cavity.
Yes.
So this is my conductor.
So what would be the electric field that we calculated using those two Gauss surfaces?
What will be the electric field? Well, you see, this is an example in which the Gauss law is true, but useless in obtaining the electric field.
For the second one or first one?
For both of them. I have no idea what the electric field would be. Electric field is, I mean, Gauss law is true, but I mean, just calculating the electric field for an arbitrary, such an arbitrary shape would be, I mean, you have to do it numerically. So I have absolutely no idea what the electric field is.
I think it should be inside both of them should be inside it. Like the first blue one should be like just inside the surface, and the other one should be inside it and contradicting the cavity as well. So I think for the second one, would we see an electric field?
I mean, you see, if this is, let's say, the whole thing is charged, okay? The whole thing has some charge, let's say plus Q. Both the red one and the blue one will see an electric field. It won't be zero.
For the second one, I said,
For both of them, for everything. There will be an electric... You see, if there is one Gauss, a third Gauss surface, let's say, here, just over here, this Gauss surface will not see an electric field. Inside the conductor, there's no electric field, whatever the shape. The other Gauss surfaces, they will see an electric field. What will be the electric field? I have no idea.
I'm going to bring the last fourth electric Gaussian surface, which is along the surface, but also at a point constant.
So this one.
So I think it will experience something like that.
No. No. First of all, there won't be any electric field in this surface because in this cavity because there is no charge in the cavity. So there's no electric field over there. All the charge in the conductor is on the surface of the charge. It cannot be on the inside. On the outer surface.
The charges on the outer surface have nothing to do in a cavity.
No.
How come there's a distance?
Well, let's see. Okay, first of all, electric fields have to start from some charges and end at some other charges. So why not have an electric field, this electric field line of this shape? Or let me just redraw it. Let's imagine we have such a cavity. And why not have an electric field over here in this direction? Let's say somehow you can imagine that there is a positive charge trapped over there, a negative charge trapped over there. So these positive and negative charges, they will attract each other. So to neutralize this electric field over here, electrons need to move from here to the other side, but the electrons will be attracted to the positive charge, so they will not be able to go to the positive charge, and hence we should have some electric field on this very narrow gap, right? No, this is not right. Even this doesn't happen. This is not, you cannot disprove this case with the Gauss law, but later on we will study some other law which says that such an electric field cannot happen, cannot exist. Even this is not allowed. So in the cavities, there's no way you can have electric fields in statics. Okay, why not? Any closed surface you can use for a Gauss surface. There is no restriction on the possible choice of a Gauss surface. Whichever, how wild the shape is, the Gauss law is still valid. You can use it for the Gauss law, the law is still valid. Any surface. Any material, inside any material, the Gauss surface is just an imaginary surface. Other questions? Okay. Yes.
Yesterday you talked about the difference between the battery and capacitor.
Okay.
And we just said that the battery is somehow has access to the voltage.
True.
I'm just saying when we see that the battery inside is so the battery inside is somehow capacitor.
No. No, it's not a capacitor. You open it up? Okay, that's great. How many of you opened up a battery? Okay, just a few? Just a few? Okay, at least it's more than what I had in the previous years. You have to, if you have to be curious, open up batteries. I know it says that will not open. You have to be careful, but you have to, curiosity, just open it up. Yes. You see, what you have probably seen is that I didn't open up my iPhone batteries, but I opened up those small AA batteries. And what you have probably seen is just some plates, right? And between those plates, there's a chemical. There's some, even if there's some paper, that paper is soaked in chemicals. And those chemicals is what is generating the potential difference. It's not a capacitor. It doesn't work like a capacitor. Even if it looks like a capacitor, it has these plates, these metals. It's not a capacitor. What generates this potential difference is the chemicals inside and the chemical reaction of those chemicals with those plates. So are you following your chemistry courses? So for example, in your chemistry courses, you don't have to hide. I know that 80% of you probably is not following the chemistry courses. But in your chemistry courses, they are talking about this so-called electronic affinity. Right? So it's something volt. Now the electric affinity of these metals are different. They have to be different metals. You cannot use the same metals. So the potential is mainly determined by the electron affinity of those materials. Other questions? Okay. Now, if you remember when we were discussing these capacitors used in electronic circuits, well, they are basically two plates, and you might roll them, but if you just roll two plates, they will touch each other. They will make a short circuit. So you want to avoid it. So usually what you do is, if you have these parallel plates, in between you put an insulator. Or dielectric. So that's what we call the dielectric. If you just put an insulator in between your plates, that is how you, in practice, you make the capacitors. Well, most of the time what you actually do is you just cause the surface of these metallic plates to oxidize. It gets oxidized, and so the oxide layer will not be a conductor, and hence you have a capacitor. So what are the insulators made up of? Okay, what is a dielectric made up of? Atoms. Atoms are made up of protons and electrons. So you have these, let's say you charge this capacitor, and then you put a dielectric inside. So what will happen to the electrons in this dielectric? It's not a conductor. It's not a conductor. They will not be able to move all the way towards the right-hand side, but all of the electrons will be displaced slightly towards the positive plate. And the protons, they will just remain where they are, or they will be slightly shifted to the negative plate. So even if you start with an atom that is neutral everywhere, so the electrons will be shifted to one side, the protons will be shifted to the other side. So you will have, the atom will be deformed, the positive charges shifting slightly towards the negative plate, and the negative charges shifting slightly towards the positive plate. So the molecules or the atoms inside the dielectric will acquire a dipole moment. Now, some of them already has a dipole moment. So if they have a dipole moment, we had seen that a dipole tries to align in the direction of the electric field. So they will, if they have a permanent dipole, they will try to align. If they don't have a dipole moment themselves, the charges will be slightly shifted, forming a dipole which is aligned with the electric field. So, of course, here there is another molecule, plus and minus. There's some over here, plus, minus, etc. Now, if you look at somewhere inside your dielectric, let's say at this point, well, we have some slightly minus charge, some slightly plus charge from the next molecule. So on the average, inside will still remain neutral. But if you look at, there will be some molecules on the surface, and when you apply this electric field, again, the positive charge will move towards the negative plate. So here we have a slightly positive charge on the surface, and there's no negative charge, so this surface over here will be slightly negatively charged. And if you could somehow measure the local charge at every point, so this surface, you will see that it is slightly negatively charged, positively charged, sorry. And the other surface will be slightly negatively charged. Well, this is the difference between a conductor, is that in the conductor, the charges are free to move. They will move until they completely cancel the electric field inside. So you won't have any electric field inside. In an insulator or in a dielectric, they are not free to move. They will not move completely to the surface, but they will be shifted slightly from their equilibrium point. And hence, one surface will look as if it is slightly positively charged. The other surface will just behave as if it is slightly negatively charged, mainly due to this shift of charges. Another way of looking at it, you can just imagine this dielectric as just a continuous material of positive and negative charges. If you put it in an electric field, what happens is the positive charges are shifted to one direction, the negative charges are shifted to the other direction. In this region, there are both positive and negative charges, so this region stays neutral. This region, there are more positive charges. Here, there are more negative charges. And again, I mean, if you like this description, again, that description also tells you the same thing. If you have a dielectric, the surfaces get slightly charged in an electric field, but this being the surfaces getting charged is not really due to the motion of the charges from one point to the other point inside the dielectric. It's not like a conductor, but it's mainly a slight shift in the negative and positive charges. A very slight shift.
How did we shift it?
We did not, the electric field did. So just imagine that you are an electron, there's a nuclei next to you, you are bound together, and then there's another electric field just pushes you in this direction and pushes the nuclei in the other direction. So you will not be broken up, but nevertheless you will be shifted to one direction and the nuclei will be shifted slightly to the other direction. It's not a breakup, as in the conductor. In the conductors, they just move independently. But there's a slight shift. So now we had this plates, which we charge negatively. Here, this is positively charged. Then we place the dielectric inside, and the surfaces of the dielectric, they acquired a slight charge. This became slightly positive, and this became slightly negative. So what is the electric field created by the charges on the plates? What's the direction of the electric field? From the right to the left or from the left to the right? That way, that way. This way. Okay, how many of you think that the electric field created by the charges on the plates only are in that direction? How many of you think that it's in the opposite direction? Okay, why? No, you see, these are the plates. So on the plates, this is where we have the plus charges. So, and the electric field is from plus to the negative. So the charges on the plates create an electric field in this direction. Let's call this E0. This is the electric field that we would have in the absence of a dielectric. But now we put the dielectric, we are putting additional charges in the system. So these additional charges will create an additional electric field. And we saw that this dielectric just behaves as if the left surface is positively charged and the right surface is negatively charged. So what will be the direction of the electric field created by these surface charges on the dielectric? On this direction, again from the positive to the negative. So let's just call them delta E. Now the total electric field will be just E0 plus this delta E. This is our total electric field. Now what can you say about the magnitude of this electric field? Is it larger than E0, smaller than E0? It's smaller because E0 and delta E, they are pointing in opposite directions. So when you sum them up, they will just cancel some of the magnitude. So the magnitude of E is less than the magnitude of E0. What about the potential difference between the plates? Now, let's say that V0 is the potential difference in the absence of the dielectric and V the potential difference in the presence of the electric. So how can you say which one is larger, which one is smaller? You see, the potential difference is the integral of the electric field. So V0 is larger than V. Well, since the electric field is getting smaller and the potential difference is nothing but the integral of the electric field, so V is less than V0. But keep in mind that we are in this comparisons, I'm always assuming that Q is constant. And Q over V is larger than Q over V0. Because V is smaller than V0. But Q over V is nothing but the capacitance. So the capacitance in the presence of the dielectric will be always larger than the capacitance in the absence of the dielectric. And mainly the reason is the dielectric will reduce the magnitude of the electric field inside. Okay, this is kind of the qualitatively what's happening. Now we have to somehow quantify it. Now the first thing we have to do is what is E? How can we relate? Well, we already know E0. E0 is just sigma over epsilon 0. We have already studied what happens if there is no dielectric. E0 is the electric field in the absence of the dielectric. Now what about E? Now E, of course, it will be a function of E0. And if E0 is 0, you would expect E to be 0. So what is the easiest function you can think of? A linear dependence. Let's say E0 over kappa. Well, you can just think of this as a Taylor expansion. We know that, well, this will be when E0 is 0 plus the derivative of E times E0 plus all the other terms. And we know that when the E0 is 0, the electric field in the dielectric is 0. So this coefficient we define as 1 over. This is called the dielectric constant. And E is equal to E0 over kappa. Of course, if you have a very strong electric field, then this term will not be enough. You will have to add the other terms to get an approximate value. But this is the first term. Here. Now we have to somehow relate E to E0. The general dependence will be highly complicated. You have to know the properties of the material, how it behaves in the electric field. And I mean, for a general E0, if you take your material, put it in an electric field, it will have a really complicated dependence. But just to simplify the expressions, I mean, you can just think of this E as a function of E0 and just make a Taylor expansion. Well, Taylor expansion, if you remember the definition of Taylor expansion, f of x0 plus the derivative at x0 times x minus x0 plus etc. You have infinitely many terms there. So just imagine f to be your electric field, x0 to be x to be your apply external electric field, and you take x0 to be 0 external electric field. So this is what you would get. But the first term is 0. If there is no external electric field, then the electric field should be 0, even if you have a dielectric. And then you have this term over here, and we just keep that one. If E0 is small enough, If you apply a small enough electric field, then this should be enough. So let's look at the capacitance. Now we have this capacitor. Inside we filled it with a dielectric. With dielectric constant kappa. We put some charge. Let's say area is A. The separation of the plates is L. Now E0 is sigma over epsilon 0, and sigma being Q over A epsilon 0. But the potential difference will not be created by E0. The potential difference will be due to the total electric field. But the total electric field is nothing but E0 over kappa. So it's Q over A kappa epsilon 0. So this will be the electric field inside my dielectric. So the potential difference is E times L, because the electric field, although there is a dielectric, it's, let's say, if the electric constant is uniform, the electric field is again uniform. So this is equal to Q over A kappa epsilon 0 L, and the capacitance is Q over delta V, which is kappa times epsilon 0 A over L. Which is in fact the dielectric constant times C0. So the effect of a dielectric that you put in a capacitor is just you multiply the capacitance by this dielectric constant. Now this dielectric constant can be huge. It can be of the order of 10 to the power 4 or even larger. So this is a way which allows you to obtain a large capacitance by using a dielectric. Just choose kappa just choose a dielectric which has a very large dielectric constant. And then you would have, even if C0 is small, even if the capacitance of your system is small in the absence of this dielectric, when you put this dielectric, the obtained capacitance will be huge.
If we have a big copper, we can have more charge.
True.
But it's always positive. I mean,
Kappa.
If copper is too large, it can be a problem.
Not really. I mean, if you want a large capacitance, there's no problem. If you want a small capacitance, you can always increase L. I mean, if you want a large capacitance, what you should do is you have to decrease L. Well, there's a limit to that you can decrease L for practical applications. Or you can increase A. Well, if you increase A, that means your capacitor is getting larger and larger. Well, if you want to keep it small and practical, in the sense that L should have some minimum value, then, and A cannot be that large. So for just practical reasons, there is a limit on the maximum value of C0 you can have. If you need a larger capacitance, just you use a dielectric.
Do we know kappa of mixed materials?
Kappa of mixed materials. Kappa 1, kappa 2. I mean, I'm leaving some empty spaces over here, but they don't exist. I'm just for separating the various regions, I give those spaces, but there is no gap over here. Just forget about those gaps. So what can we do over here?
Treat it as two capacitors.
Well, that is one way of doing it. Let's imagine we put some charge on this capacitor, plus Q over here, some minus Q over here. Well, when we were connecting capacitors in series yesterday, we already discussed that. And we can just imagine that in between, right over here, there is a minus Q charge, and exactly at the same point, there is a plate with plus Q charge. Since these two plates, the charge that we put in between this zero, it doesn't change anything. So this system with these two plates at the same point with opposite charges in between is exactly the same as one capacitor with two different dielectrics in between. They're exactly the same. So this tells me that what the properties of each one of them will be, because each capacitor just contains a single dielectric, so we know the properties. This is one way of looking at it. The second way this is our system. What is E0? E0, remember, is the external applied electric field due to these plates only. Sigma over epsilon 0 or Q over A epsilon 0. Now the electric field in this dielectric and in this dielectric, they will not be equal to E0, but let's say E1. This is equal to E0 over kappa 1, and E2, this is equal to E0 over kappa 2. Now this tells me what the electric field is everywhere. So I know that this is the externally applied electric field due to the presence of the dielectrics. The electric field in the dielectrics will be different because of the polarization of this dielectric. And inside the dielectrics, these will be my electric fields. So I know the electric fields. If I know the electric fields, I can calculate the potential difference. So let's just say that this size is L1. This length is L2. So the potential difference will be just E1 times L1. This is the potential difference across this dielectric plus E2 times L2. This is the potential difference across this dielectric. And we know what they are in terms of E0 or the charge. This is equal to Q over A epsilon 0 times L1 plus Q over A epsilon 0 times L2. This is delta V. And this is equal to Q over C. So we know what C is. So this is our capacitor, and we have filled it with a dielectric, like this one. And let's assume that this is positively charged, this is negatively charged. Well, the thing that you have to pay attention to a bit in this case is, well, let's say the charge is uniformly distributed in the absence of dielectric. Now, when we put the dielectric over there, the dielectric will be polarized, so that this side will be slightly negatively charged, this side will be slightly positively charged. Well, if there are negative charges over here, these negative charges will pull all these positive charges closer. So after we put the dielectric, the charges will not be uniformly distributed. So that is the thing we have to pay attention to. So what will happen is, in this example, we assume that the charge is uniformly distributed everywhere. So we had a single sigma, which was Q over A. Now in this problem, we don't have a uniform charge distribution. But what we can imagine is we can say that in this region, we can divide it into two parts. We can say that this region has a charge density plus sigma 1 and minus sigma 1. And the above region is plus sigma 2 and minus sigma 2. And E0 in the above region, let's say the above region, is just sigma 2 over epsilon 0. And E0 in the below region is sigma 1 over epsilon 0. Now the potential difference in the above region is sigma 2 over epsilon 0 times L. Let's call the separation L. And the potential difference in the below region is sigma 1 over epsilon 0 times L. But you see, the potential difference between these 2 points should be equal to the potential difference between these 2 points. Because here, this point and this point, there is no potential difference. They are on the same conductor. This point and this point have the same potential difference. They are on the same conductor. So that tells me that delta V in the above region should be equal to delta V in the lower region. And this tells me that sigma 2, hold on. No, hold on. This is delta V. I have to divide it by kappa over here in the below region. Because this is the E0, the external applied field. The exact electric field is this one divided by the capacitor, the electric constant. So this tells me that sigma 2 is equal to sigma 1 over kappa. So you know the charge densities in this region and in this region. Of course, if you want to, let's just assume that it fills half of my capacitor. So sigma 1 times A over 2, this is the total charge here, A over 2 because it's just filling half of it, plus sigma 2 times A over 2, this should be equal to the total charge. So this is the charge in the lower half, this is the charge in the upper half, and the sum gives me the total charge of my capacitor. Which one? This one. Well, you see, what is the potential difference between these 2 points? That point and this point. What's the potential difference? Yes, they are on a conductor. And we already know that the surface of conductors are equipotential surfaces. There is no electric field inside the conductor. And similarly, these 2 points, this one and this one on the right, they also have the same potential. So the potential difference between these 2 points should be equal to the potential difference between these 2 points. So that is why we have the potential difference in this region should be equal to the potential difference in this region. So that gives me this relation between the charge distributions in the above part and in the below part. Furthermore, I know that the total charge is Q. I just put some charge Q over there. So the charge in the below region is sigma 1 times A over 2, and the charge in the above region is sigma 2 times A over 2. The total charge is Q. And now I have 2 equations for 2 unknowns. I can solve for sigma 1 or sigma 2. Let's just solve for sigma 1. Sigma 1 times A over 2 plus sigma 1 over the dielectric constant, that which is sigma 2, times A over 2. This is equal to Q. So this tells me that Q is equal to 2 over A. No, sigma 1 is equal to A over 2 times sigma 1 plus 1 over the dielectric constant. This is equal to Q, or sigma 1 is equal to 2 over A, Q times dielectric constant divided by dielectric constant plus 1. So this is the sigma 1. Now I know the potential difference. The potential difference is this one over here. Delta V, which I can identify as delta V in the below region. This is sigma 1 over dielectric constant epsilon 0 L. This is 2 over A Q K over K plus 1. This is sigma 1. 1 over K epsilon 0 times L. This is equal to 2 over K plus 1 L over A epsilon 0 times Q, which should be Q over C. So we know the capacitance. C is equal to K plus 1 over 2 A epsilon 0 over L. Okay, whenever you have the answer, just check whether it makes sense. Okay, we put a dielectric over there, and the only property of the dielectric that we are using is the dielectric constant. And in fact, you can treat vacuum as a dielectric with dielectric constant 1. So if you replace the dielectric in our system by a vacuum, that is, if you assume the dielectric constant of the dielectric we put there to be 1, we should obtain the capacitance of a capacitor with nothing inside. If you just put dielectric constant equal to 1, this factor just becomes 1. So we recover the capacitance of a parallel plate capacitor with nothing in between. So at least it makes sense. It seems to be sensible. Of course, you can, an alternative way, by the way, of looking at this problem is you can just assume that this is just two different capacitors connected just side by side. You just divide the capacitor along this dashed line. So we have one capacitor with no dielectric in between with an area A over 2, and the other capacitor filled with this dielectric and with area A over 2. You see, this is the capacitance of a capacitor with area A over 2 and separation L, empty. This is the capacitance of a capacitor with separation L, area A over 2, but there's a dielectric with dielectric constant kappa in between. And so the system just acts as if it is two parallel plate capacitors connected in parallel. And of course, by using the same principles, you can basically imagine all kinds of complicated cases. For example, you can think of a spherical capacitor, fill half of it by a dielectric with dielectric constant K, kappa. Now the treatment will be basically identical. The only thing you have to pay attention to is that the charge density in this region on this surface will be different than the surface density in this region. And the potential difference between this point and this point will be exactly equal to the potential difference between this point and the other point. Because those points are, they are just the potential difference between two conductors. And if you just pay attention to those things, you can just solve any problem involving dielectrics. The dielectric constant, well, it mainly depends on the chemical properties. It depends on how strong the electrons are bound to their nuclei. Or what are the symmetries of the molecules. For example, if you consider the water will be a dielectric. In fact, anything that is insulator is a dielectric. Pure water is an insulator. quite a good insulator, and it's a dielectric, but it's a dielectric that has a permanent dipole moment. Because if you consider the hydrogen molecule, the water molecule, the oxygen has a larger electron affinity than the hydrogen. So the hydrogen gets slightly negative, the oxygens get slightly positive. So that's a dipole. It already has a dipole. When you put it in an electric field, the dipoles orient themselves, because in water, the molecules can easily rotate, so they will be easily orienting themselves in the electric field. So those things will affect the dielectric constant of water.
What will happen to capacitance when there is a Kelvin diode?
When there is a
Kelvin diode.
chaotic
Kelvin
dielectric.
in the diode.
What do you mean chaotic in the dielectric? A cavity. Cavity. Okay. Like this. Well, let me just use the method of separating these things into smaller capacitors. I can just imagine it as a collection of, one capacitor here, second capacitor over here, the third one here, the fourth one here, the fifth one here, as a collection of 5 capacitors. Some of them connected in parallel, some of them connected in series. So this will be basically the same thing as this configuration. I have one large capacitor here, which is connected in parallel in series with 3 capacitors, which is then connected in parallel with a third capacitor, in other words. This capacitor is the same as this one. Or if you just want to calculate the electric field everywhere, then you have to go and calculate, you have to say that the charge density in this region, let's say this is sigma 1, this is sigma 2, and this is sigma 3, plus, plus, plus. This is minus sigma 1, minus sigma 2, and minus sigma 3. And now you can find relations between sigma 1 and sigma 2 and sigma 3 using the fact that the potential difference between these 2 points and the potential difference between these 2 points and the potential difference between these 2 points should be equal. So that gives you a relation between sigma 1, sigma 2, sigma 3. You know the electric field everywhere in terms of sigma 1, sigma 2, sigma 3, and the external applied electric field, which is E0, and whichever one you like. And this one is the shortest one, but this one gives you a deeper understanding. And such problems I leave to your third year. True. True. I mean, you see, what we are, to make this identification, what we are doing is, if you put a neutral conductor here, nothing will change. It's a neutral conductor. It doesn't affect anything. It's infinitely thin. But if once we introduce that infinite conductor over there, we can just split it into 2 and move 2 conductors. We can do the same thing over here. Now, in between, I have these cases. So to obtain that one, I basically move in 3 steps. I write this as, first, a collection of these capacitors. This one is filled with the dielectric. This one is filled with the dielectric. And here there's a empty space. The above one is the same as the below one. Now, these, I can just imagine that these plates are made up of 3 pieces connected together and brought and connected by a wire. So I can just break them up. I can break them up here and connect them by wires. Again, I'm not changing anything. So here, when I break these plates, I still have a capacitor left over here, which is empty. Doesn't have a dielectric. So that's why I say that this configuration is the same as this one. That cavity just is equivalent to a capacitor with no dielectric inside. Kappa is 1. No dielectric, empty space or vacuum has dielectric constant 1. Well, for air it is almost 1. For empty space it is exactly 1. For empty space we define it to be 1. Well, in fact, most of the time what we actually do is you see, if you look at the above expressions for the electric field and the capacitance, you see, for example, you get this combination, dielectric constant times epsilon 0. Now, we usually define dielectric constant times epsilon 0 as epsilon, which is the electric permittivity. Of the dielectric. So if you have everywhere filled with a dielectric, the only difference would be just replace epsilon 0 by epsilon. And empty space is just a dielectric whose dielectric constant is equal to epsilon 0. Electric permittivity is equal to epsilon 0. Air has a electric permittivity almost equal to epsilon 0. Other questions? Okay, a 10-minute break.